Welcome to this video. We are going to learn why light refracts, and we're going to learn how to figure out which way light will bend when it goes into a new medium. First, let's make an analogy to a car driving on a road. Here's a car, and right now it's on a road, but it's headed for this mud patch. Now, when the car reaches the mud patch, it will slow down. But notice, this tire will enter the mud patch before this tire. And so, this tire slows down, while this one keeps going at the same original speed. What happens is that we now have half the car going at a slower speed and half at a faster speed. This has a particular effect. The slower tire right here serves kind of like a pivot point, and so the car turns around. The faster moving tire swings on a bigger circle, and the slower moving tire, in the same time, goes along a smaller circle. If we let a little more time pass, the car bends further, and now this second tire finally enters the mud. When the second tire enters the mud, it slows down to the same speed, and now the car just moves along the same line because both tires have the same speed again. So what we notice is that the car starts along some original path, and because it slows down, it changes and it bends to a new path. There's our summary. The same thing happens with light when it goes from one medium and slows down upon entering another medium. The thing about light, though, is it doesn't have tires. Light has wavefronts, and we show those wavefronts with these lines that look like rungs of a ladder. The wavefronts of light are similar to the wavefronts of sound. When we strike a tuning fork, a sound is produced. The sound consists of these compressions, which we draw with solid lines or wavefronts. So what do the wavefronts here indicate? They don't indicate compressions because light doesn't have compressions. Instead, they indicate the crests of the wave. So the light wave has this wavefront, and what happens is that half of the wavefront enters the water while half is still outside of the water, just like having half of the car slowing down and the other half staying at the same speed. So because the half that enters water slows down, the half right here produces this bending. So where the car originally is moving along this angle and then it bends to this angle, the light does the same thing. It begins along this angle and it bends and moves along this angle in the end. We draw just those arrows. Those are called the rays, and they indicate which way wavefronts are moving. We usually leave out the wavefronts altogether because the picture gets a little complicated. So here's our picture showing light refracting as it goes from medium 1 to medium 2. This big bold line across the middle is called an interface. It represents the boundary between the two media. So everything above this bolded line, everything above the interface, is air, or medium 1, and everything below is medium 2, or water. The dotted line is called a normal. We call it a normal because this dotted line is perpendicular to the interface. And in mathematics, normal is another word for perpendicular. Every medium has a refractive index, which is given the variable n. The refractive index measures two things. One is it measures how much light bends toward the normal. And the second thing it measures is how much light slows down. We use angles to indicate how close light is to the normal. Look at this. This is a medium angle. So light is kind of close to the normal. Down here, that's a smaller angle, so this ray is even closer to the normal. Two rules help us solve problems. The higher the value of n, the closer light travels along the normal, or to the normal. The slower the speed, the closer light travels toward the normal. Let's use that to solve some problems. Here's a question where light passes from a first medium to a second. It refracts. The picture shows us the nature of the refraction. Which medium has a higher index of refraction? The way we solve is by first remembering our rule. Next, we have to figure out which of these two rays is closer to the normal. We mark the angles. This angle is smaller, so that ray is closer. If that ray is closer, then that means medium 2, which is closer, has a higher value of n, but it also has a slower speed. Therefore, medium 1 is where light moves faster. Here's another question. We again have refraction, but now this refracted ray is not drawn in for us. We're told that medium 2 has a lower refractive index. That means medium 1 has a higher refractive index. Remember the rule. The higher n, the closer to the normal. So here, in medium 1, we are closer, and in medium 2, we will be farther from the normal. So here's the angle. We need to draw a farther angle, a larger angle from the normal. And there's our refracted ray. Number 4, light passes from medium 1 to 2 and it refracts. The light slows down in medium 2. Okay, what's our rule say? It says the slower you are, the closer you are to the normal. So first, let's just say we are closer to the normal down here and we're farther from the normal up here. The farther we are from the normal, the bigger the angle. This is farther, it has a big angle, that means we need a small angle to get closer to the normal. So there's our refracted ray. Number 5, light passes from 1 to 2. It refracts upon entering medium 2. Medium 1 has a lower refractive index. That means medium 2 has a higher n, and the higher n, the closer you are to the normal. So that means we will be closer down here. We mark the first angle, and then we draw a smaller angle, which is putting the ray closer to the normal in medium 2. Lastly, number 6. Light passes from 1 to 2, it refracts. The light speeds up in medium 2. So remember the rule, the slower the speed, the closer to the the closer to the normal. It speeds up in medium 2, which means it's going slower right here in medium 1. So this, medium 1, is where the ray is closer. We mark that angle. Now we need a bigger angle, which puts the ray farther from the normal. And that's how we... The last thing that we can do is attach two different equations to refractive index. Here's the first equation, and this is talking about the refractive index of just one medium. The second equation talks about two different media, 1 and 2, and it describes what happens as light passes from one medium to another. So the second picture here, or the second equation here, goes with this picture, and this equation goes with any one medium. Here's what the first equation says. Refractive index is equal to the speed of light in a vacuum, c, divided by the speed of light in the medium. In the second picture, the givens, in the second equation, the givens n1 and n2 are the refractive index, give the refractive index of medium 1 and medium 2, respectively, and the angles theta 1 and 2 are what we've shown here, marked. So let's do a problem. Light travels at 1.5 times 10 to the 8 meters per second in medium X. It travels at 3 times 10 to the 8 meters per second in a vacuum. What's the refractive index of medium X? We use this equation because we're dealing with just a single medium, medium X. Light isn't going from X to a vacuum. So we plug into the equation the speed of light in a vacuum and the speed in medium X, and we get 2.00 as our answer for refractive index. The 10 to the 8 cancels, and the meters per second cancel. So refractive index has no units. The second equation. Here's a practice problem for the second equation. We're given the angle at which light travels in medium A. It's 26 degrees from normal. We're also given 1.5 as the refractive index of A and 1.79 as the refractive index of medium B. Because medium B has a higher refractive index, the ray bends in toward the normal. Now we have to use the equation to find theta 2, the specific angle along which light travels in medium B. We plug in our values, 1.50 for N1, that's going to be NA, 1.79 for N2, that's going to be NB, and we plug in the angle that we're given, 26, which is the angle when inside of medium A. We divide both sides by 1.79 and we calculate the entire left to be this. To solve for theta from here, we have to take the inverse sine of both sides, and that gives us an angle of 21.6 degrees.